MEMS thermal flow sensor. The operating principle of the design MEMS thermal flow sensor is gas flow through the heat flow sensor, and the molecule of the gas conduct the heat away, and it's causing the sensor to cool and energy to be lost. Next is Wheatstone bridge circuit. A constant voltage was applied to the heater located in the bridge diagonal arm. The output of the Wheatstone bridge circuit can be expressed using the voltage law below. When the airflow passes over the heater, the bridge surface change R1 and R4. The Wheatstone bridge circuit is balanced and the output is 0 if R1 times R4 equal R2 times R3. At the right side, it shows figure 1 that the heater arranged in the diagonal arm of the Wheatstone bridge were applied with a constant voltage.
For the layout of this MEMS thermal flow sensor, we have used one substrate, 3 poly 0, 1 poly 1, 2 poly 2 and 2 anchor 1, and there are 14 steps of process definition. This MEMS thermal flow sensor consists of 7 materials, which is silicon, gold, silicon nitride, chromium, platinum, glass and boron with related elastic moduli, Poisson ratio, density, thermal expansion coefficient and relative permittivity.
This slide is referred to our MEMS fabrication simulation. The process definition. The process definition has 14 steps in it. The first step is wafer silicon. The second step is implant boron. The third step is etch silicon. The fourth step is deposit silicon nitride. The fifth step is etch silicon nitride. The sixth step is deposit chromium. The seventh step is etch chromium. The eighth step is deposit platinum. The ninth step is etch platinum. The 10th step is wafer gold. The 11th step is etch gold. The 12th step is deposit gold. The 13th step is etch glass. And the final step is wafer bonding. The material color used is shown. The final 3D model of our fabrication. This is the cross section of our final 3D model, which is from B to B prime. The final cross section is shown in the figure below.
This slide represents the ANSYS engineering data, which is the geometry, model, and setup. For the analysis system, we are using a static structural, which is there is 7 engineering data, geometry, model, setup, solution, and result. And then there is a geometry, which is we using a space claim. We import from the MEMS Pro file, and then for the model, for the static structural, we apply a fixed support and hydrostatic pressure, and the solution is total deformation and equivalence stress. And there is a mesh and input and boundary condition. This is the ANSYS solution, which is the result. At the first picture is the total deformation, where we apply the hydrostatic pressure at the left, and then the bottom picture is equivalent stress, and we also apply it at the same part with the total deformation. And for the graph, we have a 2 graph. The first one is total deformation versus fluid density. It shows that when the increase the fluid density, the total deformation will be increased. But for the equivalent stress, when the fluid density is increased, the maximum value of the equivalent stress become low.
MEMS thermal flow meter for campus sustainability. Thermal flow meter is to measure the flow of a fluid in a pipe by using thermal properties of the fluid. A measured amount of the heat is applied to the sensor heater in a typical thermal flow meter. Some of the heat is transferred to the following fluid. The amount of the heat loss is determined by the sensor temperature measurement. The transmitter calculates the fluid flow based on the heat input and the temperature measurement. The vast majority of thermofluometers are used to measure gas flow. The new age of environmental awareness that has spawned greenhouse gas initiative, which resulted in a rewriting of the rules of measuring greenhouse gas emission, which is there is now need to measure greenhouse gases in applications that formerly may have gone unnoticed. Many of these applications present opportunities for thermofluometer, including measurement and recovery of landfill gas, monitoring of flue gas, measurement and monitoring flare gas flow. Thermofluometers are unique and suited to make this measurement because they can accurately measure different mixture of gas, and because their insertion technology allow them to handle the large pipe size. MEMS thermofluometer for campus sustainability. The Sustainable Development Goals is to create a thermofluometer with fast response time and excel at measuring low flow rate. MEMS sensor also can be the solution for the campus sustainability for environmental applications such as the development new sensing principle, design and simulation, fabrication and integration technology, new smart sensor and device, Internet of Things sensor module, and also the testing and characterization of such system. There are advantage and limitation for the thermofluometer. The first one is the advantage. The thermofluometer have fast response time, and they also can handle some difficult to measure the flow and provide a direct means of measuring mass flow. And the limitation of the thermofluometer is they are used almost entire of the gas flow measurement. They have difficulty measuring liquid flow because of the slow response time involved in using the thermal principle on liquid. And the second limitation for the thermofluometer is their accuracy.